This is the last of a 7-video series on hypothesis testing, 2 standard deviations. Here's an example. Suppose we wanted to claim that the number of games attended by Red Sox fans varies more than the number of games attended by Yankees fans. Before we get further into this claim, let me explain what this would mean. Every Red Sox fan attends a certain number of games, and that population of Red Sox fans has a standard deviation in terms of the number of games attended per fan. Likewise for the Yankees. What this claim is saying is that the population standard deviation for number of games attended per fan by the Red Sox is larger than that of the Yankees. And we're going to investigate this claim with a test with a significance of 1%. What does that mean? Well, that has something to do with what's called a type 1 error or a false positive. Suppose we were to take a sample of Red Sox fans and a sample of Yankees fans, compute the sample standard deviation for each one, and suppose we were to find that the Red Sox standard deviation is significantly higher than that of the Yankees. Then that would tend to lend credence to this claim, and depending on the degree of separation, it may be sufficient evidence to support the claim. But anytime a sample statistic supports a claim, there's always the remote possibility, although we never know one way or the other, but there's always the possibility that the claim may not actually be true, but that there was some aberration in the sample, some way out there sample that just by chance made the claim look true when in fact it wasn't. We call this a type 1 error or a false positive. So when we say we're going to test the claim with a significance of 1%, we're saying that we're only willing to accept up to a 1% chance of false positive as proof that this claim has validity. So here are the sample data that are collected. 25 random Red Sox fans were chosen. The sample standard deviation was computed as 3.8 in terms of the number of games attended per fan. The same was done with 60 Yankees fans, and you can see that the sample standard deviation is lower. The question we have to address is the Red Sox sample standard deviation significantly higher than the Yankees fans to the point where we can say with a significance of 1% that this claim is actually true. Here's a symbolic representation of the standard deviations from the samples. And let's begin our 5-step process of testing our hypothesis. As usual, the first 2 steps have been done for us in this example, and that's typically the case if you're a statistics student, that the first 2 steps are essentially the given information in the problem. You won't be more than likely doing your own research. Step 3, or step 1 for us, we have to adopt a mindset of equality. We have to, in a sense, assume the opposite of what it is that the claim is saying, in the following sense. If we want to show that the Red Sox fans' standard deviation for a number of games is more than the Yankees, let's assume, in a contrary fashion, that the 2 standard deviations are actually the same. Now, of course, we don't know this to be the case, but it brings the question, why do we do this? Well, we do this because if we make this assumption, which runs contrary to what it is that we're ultimately trying to show, if we make this assumption and our sample data show a difference in standard deviations that would have been unlikely to occur by chance, then that will cast a shadow over this assumption known as the null hypothesis, and will then turn our favor towards the alternative hypothesis that the standard deviation for Red Sox fans is actually higher. So that's the plan. Let's get to the mathematics by looking at a sampling distribution. Now this looks somewhat like a normal distribution, but as you can tell, it's slightly skewed to the right. And what we're going to see in this problem when we're doing a hypothesis test regarding two standard deviations is that we have to look at something called an F distribution. More on that in a minute. But what mathematicians and statisticians have discovered is there's this computation that you can look at a distribution for and tell a lot about how likely a certain sample is to have occurred. And this is what the discovery was. In situations like this, when you have two sample standard deviations, mathematicians and statisticians have discovered that if you divide the larger of the two standard deviations by the smaller of the two standard deviations and square that quantity, you get a very mathematically usable distribution that you can see here that we can deduce probabilities from. Now, you can look at our particular sample and notice that the larger of the two standard deviations is 3.8 and the smaller is 2.6. And that's what we mean by large and small. But this distribution goes beyond our particular sample. This is really a more general statement. A sampling distribution gets the idea to you that if we were to over and over and over again repeatedly do this exact same sampling, by that I mean if we were to take 25 Red Sox fans and 60 Yankees fans and continue to do that sample many, many, many times in a row, and if we were to plot out the square of the ratios of the standard deviations as shown in this formula, that we would get a distribution that would look something like this. The question that we have to ask ourselves is this specific sample somewhere in the middle of the distribution, not far off to one side? Because if that's the case, then it wouldn't be unusual for the square of the ratio of standard deviations to fall there. But if we get a very large F value way over here to the right of the curve, then it's reasonable to assume that that wouldn't have happened by chance and that we must have made a false assumption in our null hypothesis. And again, that would lead us to the claim that we're trying to prove. So here comes the actual computation of the probability that the discrepancy of standard deviations could be as large as we see here if the two population standard deviations were actually the same. So since our claim is regarding two standard deviations, it turns out we're not going to look at standard error. It's a non-issue here. Our test statistic is the same F calculation shown above, and we're going to use this F distribution along with the F cumulative distribution function to determine the probability that in a world where the standard deviations actually were equal, we could get as big of a discrepancy as 3.8 and 2.6 as we did in our particular sample. So, plugging in all the numbers from the problem, will get us here, where the F cumulative distribution function will give us the probability of such a discrepancy in sample standard deviations. So it's worth noting that the 24, which is referred to as degrees of freedom 1, is one less than the sample size. Let me explain further. Notice that in the Red Sox sample data, there were 25 fans. One less than that is 24, and that explains this degree of freedom. Notice also in the sample data there were 60 Yankees fans, and one less than that is 59, which explains the degrees of freedom 2 here. But the question that you should be asking is which degrees of freedom goes first, because it isn't necessarily the order in which they're listed in the problem. Yes, in the sample data here, I happen to mention the Red Sox first, but that didn't determine the order of the degrees of freedom in my cumulative distribution function. What determined that order was degrees of freedom 1 is always related to the sample size of the sample that had the larger standard deviation. In other words, 3.8 is bigger than 2.6. 3.8 came from the Red Sox, and therefore, since that is the larger of the standard deviations, I used their degrees of freedom first, 24, and the Yankees second, 59. So, plugging this into a calculator or any other type of software or app will give you 0.0094, a slightly less than 1% probability of a type 1 error, or probability of a false positive. That is the meaning of that number. So on to step 5, which is really our third step as a student. Comparing that probability of type 1 error to the significance that we set out in the first place as our threshold will ultimately lead us to decide whether this claim is to be accepted or not. And as usual, since the probability of type 1 error is less than 1% or less than the significance, then we would state that there is, in fact, sufficient evidence to support the claim that the Red Sox fans' attendance varies more than that of the Yankees fans. Let's take a look at a second example. Suppose factory A and factory B both produce aspirin pills, and we're claiming that factory A produces pills that vary less in their mass than that of factory B. A side note here, despite any factory's attempt to make all their products exactly the same, there are very, very minor variations in the manufacturing process that would cause something like one aspirin pill to weigh slightly more or less than another. So we're going to test this claim with a significance of 5%. And before I go on, I'd like to take a brief detour into significances, a little bit beyond what you might be studying in your class. Did you notice in the last problem about the Red Sox and the Yankees that we tested that with a 1% significance? But here, when it comes to the amount of medication in a pill, we're testing it at a 5% significance. That seems a little backwards to me, because as it turns out, the lower the significance, the higher the certainty, or the higher the bar or threshold of proof that you have to attain. And see, I think we could all agree that the medicine from pill to pill not varying too much is more important than knowing how much variation there is among baseball attendance. Now, why did I have a 1% significance in the last problem and a 5% significance in something that seems much more important than baseball? Well, honestly, just because I put random numbers in the problem. And as a student in a statistics class, you won't care. You'll just test to the claim of whatever significance the professor puts in the problem. But when you get into the real world, the choice of significance ultimately depends on the seriousness of whatever it is you're studying. That aside, let's get back to the problem. Here's our sample data. Factory A, 6 pills were chosen at random from them, and there was a sample standard deviation of 10 micrograms. Another side note, a microgram is only 1/1000th of a milligram, so that's not much variation as you would expect in a pill manufacturing plant. Factory B, 17 pills were chosen at random, and you can see that the sample standard deviation there is double. Now this claim is saying that factory A varies less than factory B. And the sample data, on first glance, does tend to support that theory. After all, factory B had twice as much variation, as you can see. But let's do the mathematics and not let our gut feelings be our guide here and see how this claim plays out. Here are the symbolic representations of the sample data. So back to our 5-step process, and starting with step 3 as usual, let's assume, contrary to what it is that we're trying to prove, that the two factories have exactly the same amount of variation from pill to pill. In other words, that the population standard deviations are the same. We do this the same reason we always do, because if this assumption can lead to a questionable outcome, then we can question the assumption and thus prove what we want to prove. So our null hypothesis ultimately is something that we adopt briefly in hopes to dispel it later and accept the alternative hypothesis, our ultimate goal. So let's look at the F sampling distribution again, which is what we look at when we're comparing two standard deviations. And again, this calculation for F is not just referring to the 10 and the 20 in our particular sample, but what we're imagining in a sampling distribution is that this exercise of taking 6 pills from factory A and 17 from factory B, we're imagining what would happen in a theoretical sense if we repeated that sampling over and over and over again to the point where we had a good view of how this calculation, the square of the ratios of the sample standard deviations, would spread out. And our question, of course, is right here, is the fact that the sample standard deviation of factory A is literally half of that of factory B. Is that enough evidence to support the claim that A varies less than B? Well, if our F value falls here, relatively low, then no, but if with a high enough F value, we will be able to support this claim. So on to our second step, or fourth step overall, the mathematics itself. Same formulas as before. In this particular case, we plug in the two sample standard deviations. Remember, the larger of the two is always your numerator. It doesn't matter what's mentioned first in the problem. You always want to get an F value bigger than 1. In this case, F is 4. Now, that number in and of itself doesn't mean much to the average person, but what's important about calculating F is that we can then plug it into the cumulative distribution function. Again, I'd like to point out that these last two numbers, the 16 and the 5, are degrees of freedom. And let's analyze which goes first, because order definitely matters in the cumulative distribution function. In this function, I put the 16 first. Here's the reason. 16 is 1 less than 17, which is the number of pills that we took from factory B. But I didn't put that first because 17 is larger than 6, or because I took more pills from factory B. I put that first because factory B had a larger sample standard deviation. 20 is bigger than 10, therefore factory B has the bigger standard deviation, and therefore that degrees of freedom goes first, and the degrees of freedom from the other data goes last. Typing this in a calculator or any other software or app will give you about 6.6%. What does that mean? It means that the fact that the sample standard deviation from factory A is half that of factory B, that fact that there's such a big difference in standard deviations means that there's only a 6.6% chance that this sample happened by statistical accident. It's more likely that this sample happened because factory A actually has less variation than factory B. But we set out to prove this claim with 5% significance, meaning the probability of a type 1 error or false positive had to be less than 5, and we didn't achieve that threshold that we set out to. But despite the fact that the evidence does lean towards the claim, because 6 is greater than 5, we are forced to say that there is not sufficient evidence to support the claim that factory A has less variation than factory B. Might it actually be the case that they do? Certainly, but this particular evidence in this study doesn't show it. And that completes Lesson 7 of 7 and this video series.